Now that we've had our reminder of how to actually graph a line, now we're going to do some more solving systems. So just like in grade 10, we had been able to graph two lines and see where they intersect. Well, when we talk about inequalities, we're really going to be talking about the intersection of their shaded region. So a system of linear inequalities, yeah, linear inequalities that are graph same coordinate plane, the intersection represents the solution. So it's more specifically the intersection of the shaded regions. Now today we're going to work with putting a word problem into linear models and then graph them to determine solutions. We're going to be using what are known as let statements. So we had already kind of talked about that a little bit in the first section. We're going to talk about that even more. At the same time, we're going to be talking about converting word problems into equations. So the first thing, first example, sorry, company makes two types of boats. Different assembly lines. There's aluminum fishing boats and fiberglass boat riders. When both assembly lines are running at full capacity, a maximum of 20 boats can be made in a day. So when they're fully running, you can have 20 boats made at a maximum. But the problem is, it's not really the problem, but a stipulation is that the demand for fiberglass boats is way greater than the demand for aluminum boats. So in order to make assumption or make coordination for that, the company makes at least 5 more fiberglass boats than aluminum boats for each day. What combinations should the company make each day? Then we're going to graph to show each possible solution, and we're going to check our answers. So first things first, let's talk about, okay, we have two things. We have two stipulations. In other words, we actually have two equations. So when they're both running at full capacity, a maximum of 20 boats can be made. So when I talk about let statements first, we're going to say, we're going to use some variables. In this case, A and F probably would work the best. A for the aluminum boats, and F for the fiberglass boats. Obviously, we're not going to use the other variable for the other type of boat. We could use X and Y, but let's use some variables that actually make sense in the situation. So our first equation says when they're running at full capacity, a maximum of 20 boats can be made, which means that the total amount of aluminum boats and the total amount of fiberglass boats can be a maximum of 20. The way that we'd have to write that is that however many aluminum, if we add the amount of fiberglass, it would have to be less than or equal to 20. So that's all that is. The demand for fiberglass boats is greater than the demand for aluminum boats. So the company makes at least 5 more fiberglass boats. So let's put that in context. If you have, let's see, if you have 7 fiberglass boats, all right, let's see, let's put that in the right spot. Sorry, I'm using A. You can make 2 aluminum boats, or 1, or 0. So the reason I'm doing that is to help illustrate what our equation is going to be. Meaning, the demand for fiberglass boats is greater than the amount of aluminum boats. So you can make at least 5, so I mean it could be equal to 5. But if we take the amount of aluminum boats, we add 5 to it, then it could be equal to, at the same time, the fiberglass boats could be greater. And if we go back to these numbers, 7 is greater than or equal to 2 plus 5, 1 plus 5, or 0 plus 5. So overall, if you have a lot of situations, you have to pay attention to where does something like that play into effect. Now, let's do some graphing. Now you may ask, well, how am I supposed to graph this? The problem or the thing that we need to do is identify how are we going to graph it. Because this equation already has one of our variables by itself. And normally, we try and put things into y equals mx plus b form. Well, this equation is almost identical to this. The only differences are the inequality, and we don't really have y's and x's. We do have a 1 in front of our a, which means that that's going to be our slope. But because of the form that it is, it means that our fiberglass boats can be written on our y-axis. The f is our y, which means that our a value will be our x's. This one we can graph nicely. For example, I know that I have 20 squares here. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Have that on both sides, I believe. 5, 10, 15, and 20. Therefore, that's 0. Great. Doesn't always have to work out that your x's and y axes are going to be identical, because this could be going up by 10s, this side could be going up by 1s, as long as each individual axis is consistent. If we're going to graph this one, because it's already in a nice form, we're going to use a slope of 1 and a y-intercept of 5. So for this one, let's graph it in purple. Y-intercept of 5, slope of 1 over 1. Sorry, I should probably make those dots a little bit larger, just to make them a little more visible. Now we have to ask ourselves, how are we going to actually connect these dots? Well, let's see. It's a greater than or equal to, which means that it's going to be some kind of solid line. But now we have to actually think about what kinds of boats can we have? Are we going to have a real boat, an integer boat, or a whole boat? Well, it doesn't make sense to say that, oh yes, I have 1.5 boats. No, you have one boat and an unfinished boat, which means you have one boat and something that's not a boat, which means the A and the F can only be part of the whole numbers. You can't have negative boats made. You also can't have 1.5 boats made. It's not, half a boat is not a boat, which means our graphing here is just going to be the dots. And that's all that's going to be. That's all that we can do. Now in our other equation. Now before we get into the shading and all that, we'll deal with all this. Let's do the graphing first. Because this equation does not have one of our variables completely isolated, we're going to have to get one of them isolated. Because this one already has our y variable, which is the f, by itself, we're going to do the exact same thing to this one, which means I have to subtract a from it, which means the f is going to be less than or equal to negative a, add 20. Notice how I did not divide by a negative, I just subtracted. Therefore, I can graph this one. Y-intercept of 20, slope of negative 1, which means when I graph my dots, I can continue all the way down here. No, scroll down a slight bit more. Now let's talk about where are we going to be shading. Now since I'm already in the red one, let's talk about this. So the fiberglass has to be less than or equal to. Now I've already talked about why I'm not using a complete solid line. It's because they can only be part of the whole numbers. But being less than or equal to means that we're going to have to be below this line. Well, below that line means somewhere down here. Now I'm going to do this, but I'm not going to say that you're going to have, just bear with me. Now, because we know whole numbers, we'd actually be using the dots, but this is the region that we would be shading. Obviously, we're not going to be using a shade, but we would be using dots. So that's to illustrate that we are below that line. In this one, we have to be greater than this line. Well, greater than this line means above here. It is actually above that line. Well, how can I say that I am both below this line and above this line? It's this triangle here. Oh, that's my arrow. So to say I'm there, I'm going to fill in my solutions as being all of these values. Now, obviously, it would kind of come down to here, but we have each of these points as one, so we're not going to be putting some kind of point here. This would be 7.5 and 12.5, not a boat. Now I'm just going to go a little bit overkill and add in all of the dots, but really indicated that you're in this region and making sure that you have your dots filled in, saying that you're still here, you're still into this area. Actually, no, sorry, that's not good. Let's use these. Fill in the dots, say that you're still below this line, but above this line. That's really good enough for me. But you have to indicate that it is the dots. You can't be doing that. Now I'm going to go overkill and I'm going to fill in every dot. Just give me a second. And there we have it. Those would be all of our possible solutions. So if I say, what kind of combination can you make? Well, any of these would work. I could say this one, which would be 3 aluminum boats and 13 fiberglass boats. Oh, 2 S's in fiberglass. Why? Because we're going to check. 3 plus 13 is for sure less than or equal to 20, because that's 16. And our fiberglass boats is 13. It's for sure greater than or equal to 3 plus 5. So those all work. That's one possible solution. Obviously, you can tell that there's multiple possible solutions. And there's our first example. A sloop is a sailboat with 2 sails, a mainsail and a jib. Oh, that is definitely not a sail, right? My job, a jib. When a sail is fully out or up, it is said to be out 100%. When the winds are high, sailors often reef or pull in the sails to be less than their full capacity. Because obviously, sails are out at full capacity, you're going to be going a lot faster than you may be comfortable with, and hopefully that's common sense. Jim is sailing in winds of 22 knots, or about 41 kilometers per hour, so he wants no more than 80% of the mainsail out. Jim also wants to have more mainsail out than jib. What possible combinations can Jim have? We're going to graph and determine some solutions. So again, we're going to have 2 let statements. Obviously, M is going to be talking about the mainsail, and J is going to talk about the jib. So again, we have 2 things that we're going to graph. Jim is sailing 22 knots, so he wants no more than 80% of the mainsail out, which means the mainsail would have to be less than or equal to 80%. Jim also wants more mainsail out than jib. So the mainsail would have to be greater than Jim. Those are our two equations. So our question of, okay, what kind of things can we do? Well, I already have the m's already on the left-hand side, so it probably makes sense to have m as our y-axis. Therefore, j would be the x-axis. Every single point here is worth 1. Oh, sorry, that's not correct. Every single one is worth 10, because we're going to talk about percentages. So the m has to be less than or equal to 80. Well, the m is 80 right here, but it's also 80 all along this horizontal line. So let's take a look at what our variables mean. Main and sales jib. Well, they're also talking about percentages. What kind of number system are we going to be concerned about? Well, can we have whole numbers? Yeah, we can have whole numbers. We can have 0%. Can we have negative numbers? Oh, no. We can't have a negative percentage of sale. Can we have a decimal value? Yeah. We're going to have technically 56.5% of the sale out. So because we have positive numbers, but we can also have decimals, we say it's the real numbers, but it's the positive real numbers. What type of line are we going to graph here? Because it's 80 all along this horizontal line, we can actually use a nice solid line because all of our values actually make sense and it's less than or equal to. So I'm going to start off with a little bit of the graphing idea. Because we have to be less than this, we'd have to be shading or dotting. We'll see which we're going to talk about in just a second. We'd have to be below it. So I already did this one in blue. I'll do this one in purple. The main has to be greater than j. Well, that means our y-intercept is 0. I'm just going to move that over there. Our slope is 1. So our y-intercept is 0. Slope is 1. And we're going up and over. Now noticing though, again, that each of these is worth 10. So up 10 over 10 is the exact same thing as going up 1 over 1. What type of line are we going to graph? Well, it's going to be greater than j. So to be greater than j, any value that is on this line would not be counted, which means we would have to have, oh, sorry, I want a line, not, there we go. Yeah, I want, oh, come on, I want a dashed line. Where are you? There you are. So this is indicating that any value that would be on that line would not be counted. At the same time, I'm going to make sure that that line continues on. Obviously, anything below would not make sense. And I forgot about my arrow there. And I'm just going to quickly go back and fix these two as well, because that one's good. This one, technically, those points do continue on forever. Sorry about that. If we're going to talk about all these values, how are we going to shade? Well, m is greater than j. Well, where is greater than this purple line? Greater than is above here. How are we going to shade? Because we can have decimal values, because we can technically have 0.1%, we'd actually be able to do a nice solid shading. While keeping in mind at any value that would be on this purple line would not be considered. All right. It's a good enough sketch. Because what we're concerned about is what possible combinations can Jim have. Any of these values, we cannot have this one. We can't have 50 and 50 because that means that we have 50% of the main and 50% of the Jim. But 50 is not greater than 50. It's greater than and or equal to, but it's not greater than. So this one would have to move even into there so that it's still above that line. So let's see, what would that be? If we rough estimate 47% jib, 50% main. Does that fit? Is 50% less than or equal to 80? Yep. Is 50% greater than 47%? Yep. So this is one possible solution. Same time, there's technically an infinite amount of solutions in here because decimal values produce infinite amounts, but that's another discussion. So we've determined some possible solutions and we've checked it. And our last example. A nursery school serves morning and afternoon snacks to its students. The morning snacks are fruits, vegetables, and juice. The afternoon snacks are cheese and milk. Obviously, if you're in some kind of nursery or daycare or anything like that, you have to have nutritious snacks. It's actually part of their mandate and part of government funding is to have nutritious snacks. Which also means that you should probably be doing the same thing at lunch. Anyways, school can accommodate 50 students or fewer altogether. Students can attend for just the morning or for a full day. The morning snacks cost $1 per student per week, and the afternoon snack costs $2 per student per week. Obviously, this might be lowballing, but it's just a question to help us understand. The weekly snack budget is $120 or less. Oh, left. So let's talk about what kind of variables we can use. We can talk about morning students or full day students. Morning or full day. So it says that the school can accommodate 50 students or fewer altogether. So meaning the amount of morning students, the amount of full day students could be less than or equal to 50. So that's one of our equations. I'm actually going to just change the color on the next one just to make it more colorful. The morning snack costs $1 per student per week, and the afternoons cost $2 per student per week. That does not mean this. For every morning student, it would be $1. For every afternoon student, and the budget is less than or equal to 120. This is not the case because if a student is attending full day, so a full day means morning and afternoon. If you have attended for the morning and afternoon, a full day student would technically cost $3 per day. So this is the correct equation. This is the one that we need to use. So now that we have this, we should be able to graph. Not sure what the heck this is. I'll fix that on future copies. But each of these doesn't really matter. Why? Because we're just going to have one of our equations manipulated for one of our variables. Again, doesn't really matter which one. For example, I have my m's kind of already by itself. It probably makes sense to just subtract my f's over. Subtract the 3f on this one, meaning I'd have m is less than or equal to a negative f plus 50, for m being less than or equal to negative 3f plus 120, sorry. And these are the two lines that we can graph, which means m is our y-axis, f would be the x-axis. If we graph this one, we'd be starting at 50 and going with the slope of negative 1 over 1. So let's see, how many squares do I have? 4, 8, 12. Okay, awesome. And I think that this one's probably the same, 4, 8, 12. Wow. Which means it'd be 40, 80, and 120. Alrighty, 50. So from 50, I'm going to be using a slope of negative 1 over 1. So down 1 over 1, Now, because this is kids, I'm for sure going to keep it dotted. Yes, absolutely. Technically, we'd have about 10 dots in here as well. I think I probably have a lot less. Because these are all talking about kids. And on our other one, we have a y-intercept of positive 120, and we have a slope of negative 3, or negative 3 over 1. So because each of our axes are going up and down by the same amounts, like 10, 10, 10, 10, 10, 10, 10, 10, we can read it as down 3 over 1, being the same kind of idea. Down 3 over 1, down 3 over 1, down 3 over 1. Awesome. Now, where are we going to shade? Well, both of them say less than or equal to. Less than or equal to both of these lines. And again, these ones technically are really dotted, not dashed. Sorry, I'm just going to delete that part because that definitely looks like it's dashed. It's dotted. But below this, where is below this purple line and below this one? Well, it's in here, which means our solutions would include anything that's on this line but also any ones that are in here. Now I'm using the intersections. At the same time, technically, I could also use all of these dots in there. I'm not going to shade it because we're dealing with kids. Half a kid is not a kid. You have manslaughter on your hands, at least. Sorry, inappropriate joke. But we have less than both of these lines. So what are some possible solutions? Well, if we have full day kids, morning day kids, let's deal with it. See, this one, what is that point? That would be 30 full day and 10 morning. Does that mean that the amount of morning and full day is less than or equal to 50? Yeah. 10 plus 30 is for sure less than or equal to 50 because 40 is less than or equal to 50. If it costs $1 for every single morning kid, so 1 times 10 morning kids, 3 times every single full day kid, being less than or equal to 120. 10 plus 90. Absolutely, 100 is less than or equal to 120. So both of those work. This is one possible solution. And now that we have a little bit of understanding of what some possible solutions are, you can go have some fun.